Alright class, for lecture 20 I uploaded these sample problems to the Blackboard and I would encourage you to solve them before looking at the solution. So I'm gonna do the solution here, but the PDF without the solution is uploaded. And then I will upload the solution once I finish recording this video. So problem 1 is consider the heat conduction problem in 2 dimensions with the conduction specified by this PDE, where so the divergence of the conductivity matrix times the gradient of the temperature, which is the flux, plus some source term equals some constant times some temperature proportional to the temperature at the reservoir, which is T infinity. And then boundary conditions are defined here. So this is basically, this is the PDE that we need to solve. This is the natural boundary condition, and this is the essential boundary condition on some domain omega in 2D. And the question is to find the the question of the problem is to find the temperature field, where D is the conductivity matrix, as I said, S is the source term, H is the thickness of the plate, T infinity is the temperature of our reservoir, and the question that we are asked is to state the weak form. And then as a help, we are told the divergence theorem and Green's formula. And if you remember how to go from the strong form to the weak form, it's always the same strategy. So let me sort of go blank. So let's do problem 1. Let me rewrite. So divergence of sigma or of Q, which is the flux, plus the source term equals to H T minus T infinity. That's the PDE that we need to solve, with Q equals gradient minus D gradient of T. I may have made a mistake up here. Yes, so I'm missing a minus here. Q equals minus D gradient of T with boundary conditions Qn equals Q dot N equals some value on gamma Q, and temperature equals some value T bar on gamma T. So that's the strong form. All of this together is the strong form of the problem. To go from the strong form to the weak form, remember the first thing is going to be multiplied by some weight function, everything. So we're going to multiply everything by a weight function. And we're going to integrate over the domain. Now this is not a really good notation, so I'm going to move everything here on the right hand side to the left hand side so that it actually makes sense. So what I'm going to end up with is going to be integral over omega of W omega times the gradient, the divergence of the flux plus the source term minus 2H T minus T infinity. So now this makes sense actually. So that's the first step. And then the next step is going to be the integration by parts equivalent in 2 dimensions. So this is multiplied by weight function and integrate. Then I'm gonna put in quotes integration by parts for 2D. That's Green's formula. And similar to the 1D case, we don't need to use the integration by parts in all the terms. The only term that we care about for the integration by parts is the one that has the double derivative. And that one is this term right here. The divergence of Q is the one that has, because Q is the gradient of temperature, this divergence of Q is essentially the second derivative term on the temperature. So that's the only one that I'm gonna that I'm gonna put aside here. The other ones I'm gonna put in a separate integral. So here I'm gonna have s minus 2h t minus t infinity d omega equals 0. And so I need to use Green's formula here. You can go back and see what is Green's formula. Basically, if you have the integral of w times the divergence of some vector field, that is the same as the integral over the boundary of w times the normal component minus the integral of the gradient of the weighting function, or in this case just function w times the vector field. So that's it. That's really all we need to do. So we basically copy that here, and what we're going to end up with is the integral over the boundary of w times the normal component of the vector field over the boundary minus the integral over the domain of the gradient of w times the vector field. And then the rest we keep as we had. So omega times s minus 2h t minus t infinity the omega, all of that equals 0. So that's it. We just used Green's formula. Then the next step is going to be the incorporation of the boundary conditions. Pausing here for a sec, this is the same structure of what we did in 1D. Multiply by weight function and integrate, do the equivalent of integration by parts, then use boundary conditions. And then similar to the 1D case, for the boundary conditions, t equals t bar on gamma t, right? That's what we know. We know Qn, that is the normal component of the flux, equals some value q bar on gamma q. And we know because of this, we know that for the essential boundary conditions, w equals 0 on gamma t. We don't know anything about w in the other part of the boundary, but we definitely know that on the essential boundary condition, w will vanish. So if we use that here, this integral right here is an integral over the boundary. Let me draw my domain again. So this is omega, and the omega domain has some part of the boundary, which is gamma t, where we have the prescribed temperature, and some part of the boundary, which is gamma q, where we have the flux. The flux is defined in gamma q. And the sum of the two boundaries should be the total boundary. So this integral is an integral over the entire boundary, but I can split it into an integral over the part of the boundary that has the flux boundary condition. I'm just simplifying. Instead of qn, putting q dot n, I'm putting qn here, plus the part of the integral over the boundary that has an essential boundary condition. And then the rest I'm going to leave the same. So the only thing that I did is I split this integral into two integrals. Part of the integral over the boundary that has natural boundary condition, part of the integral over the boundary that has essential boundary conditions. So this is the part of the boundary that has essential boundary conditions. This is the part of the boundary that has flux boundary conditions. And then here we're going to use the fact that on the part of the boundary that we have the essential boundary conditions, the w equals 0. So here w equals 0 because of essential boundary condition, right? And here we know qn, that one we know it's q bar because of that. And so here this whole integral will disappear, and then here I'm gonna substitute q bar. So here I'm gonna end up with just the integral over the boundary that has a natural boundary condition times the value of the natural boundary condition, then nothing, then integral of gradient of omega times q plus integral of omega times s minus 2h t minus t infinity equals 0. That's pretty much it. We just need to state the weak form. Okay, I'll state the weak form and then I'll add a couple of notes. So here finally I can state the weak form. We have find t in the space S, which is going to be the functions t in C0 of omega with t equals t bar on gamma t, such that then this is true for all w in some other space. I'm going to call it V, which is the space of omega functions which have to be also C0 over omega with w equals 0 on gamma t. That's it. So that's the weak form. Corresponding to that initial strong form. The couple of notes that I want to add here are, one, you can substitute this q bar in terms of temperature, because here it's not clear where the temperature is except here. So technically you would have to say somewhere that q equals minus d gradient of t, or directly substitute that here, so that instead of having this term right here, you would have this term, d times gradient of t. And then this will turn into a plus sign. So that's one thing. Then the other thing that I was going to say is that this looks a little bit different with respect to the heat transfer problem that we've defined in the past. And the only difference, so that's note 1. Then the only difference is this term right here. So before we didn't have that. It looked almost exactly the same, but it didn't have this t minus t infinity. So note 2 is note that t appears in the weak form without derivatives. Without derivatives. So in the past, the only thing that we had was everything, so wq bar plus the integral of gradient of w times d times gradient of t, and then integral of ws. So that's what we had. So the only way that the temperature appeared in the weak form was with the gradient. Now we have the gradient, and we also have this other term where the temperature appears without the gradient. And if you're curious what does that mean if you actually discretize it, what it will mean is that this term right here will lead to some force term. So let me actually paste it again right here. So what it means is that this term, it's gonna end up, I'm gonna skip the steps, skip derivation. This is gonna end up with some force vector of forces q which is just going to be for a given element. This is just going to be the integral of the shape function vector times the q, right, at the corresponding gamma e. So for the triangle, this will be a 3×1 vector with the forces. For the quadrilateral, this will be a 4×1 vector with the flux forces. So that's what we will get from here. From this term, once you substitute and you get this integral of gradient of w times d times gradient of t, then I'm gonna skip the steps, but hopefully you recall that this will end up giving you the stiffness matrix. So it will give you the stiffness matrix, which is gonna be the integral over the element of the gradient of the basis functions, which we typically put in this term, in this matrix B times D times BE. So that's what this will give you. Then here, the first term, so this will split into two. So the term that has integral w s minus 2h t infinity, that term, no problem, will lead you to, actually let me also say that I'm skipping steps. That will give you the force vector from the source term, which is going to be the integral over the element of the shape function vector times s minus 2h t infinity. And this is a term that we've seen before. And the one that is different from all that we've done in the past is this last term in this integral. So there's going to be an integral that looks omega times 2h, well, minus 2h t. Right? So this one has omega and has temperature. So actually, if you introduce the shape functions, this will give you a new type of matrix that we haven't talked about, which is the mass matrix for the element, which is going to look something like the integral over the element of minus 2h and NE, I guess NE transpose NE. So the integral of the shape functions, whereas the stiffness matrix has the integral of the gradients of the shape functions. Remember that the mean matrix has the gradients of the shape functions. Here, the mass matrix will have the integral of the product of the shape functions. So that's a different type of matrix that we haven't talked about, but this is what you get when you find the temperature without any derivative in the integral of the weak form. So that was the extra note number 2 that I wanted to make. And that's it. That's it for problem 1. I'll do problem 3 in a different video, but I do want to do problem 2 here because it's kind of a trick question. So problem 2 is consider the heat conduction problem in 3 dimensions. The corresponding form is the standard strong form that we've seen with natural and essential boundary conditions. Everything is as before. State the weak form. And it is a trick question because remember that, you know, Green's formula is the same in 2D and 3D. The definitions of the gradient and the divergence generalized to 2D and 3D. So what is the weak form of this problem? Well, it turns out that it's exactly the same as the previous problem. The only thing is that we don't have the extra term, right? So this one will look the same. So we'll have, I'm gonna skip it. It's gonna be the same as before. Find temperature in some space S, which is defined as C0 functions with essential boundary conditions on the part of the boundary that has essential boundary conditions such that the integral over gamma q of omega q bar, right, plus the integral over omega of gradient omega d gradient temperature minus integral, sorry, plus integral of omega s equals 0 for all omega in the space B, which is omega in Z0 with omega equals 0 on omega t, on gamma t. That's it. So the weak form actually is exactly the same because the definitions of the gradient, the dot product, the divergence, all of that looks the same between 2D and 3D. So there's no change. So that's it for product